Hi, my name is Michael Wang, and I'm a fifth-year graduate student at Princeton Edge Lab. Today, I'd like to talk about HetNets for fifth-generation wireless networks. The demand for 5G networks really comes from two specific aspects: the network side and the user side, and their competing demands. On the network side, there is an increased demand for data from users, and the network needs to exploit additional spectrum to provide this data for services to these users. On the other hand, users wish to maximize throughput at all times, but minimize switching costs that arise due to a budget or battery life considerations, where switching costs are defined as time lost or energy spent for handover. Increasingly, companies have started to turn towards looking into spectrum above 28 gigahertz as the answer, specifically millimeter wave radio. Millimeter wave radio for fifth generation cellular networks has several pros and cons. On one hand, millimeter wave can provide much higher throughput compared to the 2.4 gigahertz ISM band and allow for increased frequency reuse. However, on the other hand, there could be frequent channel transitions between line of sight, non-line of sight, and outage states, which are hard to predict, high path loss attenuation due to water content in the human body, and also hard handover is required due to wall attenuation whenever a user enters or exits a room. The main problem we address in these slides is how exactly should a user optimally select the best access network in a HetNet scenario to maximize throughput and minimize switching costs when the user has access to millimeter wave RATs. The HetNet model we use is the following. We work in discrete slotted time where users, UEs, associate with at most one base station in each time slot. Each base station cannot provide an accurate measure of throughput to each user. This is not known a priori. Each user can see up to M base stations, and each user makes local decisions for base station association, as you can see on the right-hand side in Figure 3. This is a classic problem of exploration and exploitation, the trade-off between the two. On one hand, a user, or UE, wishes to explore. They wish to learn these unknown statistics of each base station in order to better understand which option can provide the best throughput. And at the same time, they wish to sample non-optimal base stations just to update their statistics to ensure that they're not locked into a suboptimal base station. However, the user also wishes to exploit the channels. They wish to maximize the amount of time spent on the best base station to get the most aggregate throughput, and they also wish to minimize the number of times they switch due to switching costs. The metric we use for this is regret. We compare the performance of our online algorithm with an offline optimal strategy. Since each base station's throughput is a random process, we generally take the offline optimal strategy to be chosen as simply the base station with optimal mean throughput without switches, where with mu star as the optimal throughput and defined as the throughput of the best base station. So the regret is formally defined as R alpha T, the total regret of online policy alpha that we design at time t, and it is the sum of the sampling regret R cap T alpha T and the cost of switching R cap S alpha T. The sampling regret is defined in the orange box as simply the throughput gap between an offline optimal strategy and the expected reward, the expected throughput of our own policy. And the cost of switching is the base station specific cost of switching, where CA and CD are static costs of association and dissociation, NA and ND are simply the number of times the user has associated and dissociated from that base station. We formulate the problem as a multi-arm bandit problem where a single user selects a single base station to interact with at every time interval. So basically each time the user plays an arm, receives the reward, depending on the unknown reward distribution on each arm, and if the current arm is different from the previous arm, then a cost is incurred due to switching. We assume that there exists a single base station with maximum mean throughput mu star, and that the rewards are non-negative and finite. The algorithm that we develop is called the UCB-MS algorithm, and it basically is a combination of two algorithms. First, we have the block scheduling algorithm, which determines when a user can switch between different base stations. And finally, the base station selection algorithm, which, once the user is allowed to switch, calculates which base station is the best to switch to. So the general intuition here is that the block scheduling algorithm simply groups samples of given base stations together to avoid regular and frequent switching. So the grouping is done so the number of switches is sublinear in time, specifically little o lnt, and the base station selection algorithm is in essence a form of an upper confidence bound type algorithm, where we calculate a sample mean over a fixed number of samples and add an exploration term to encourage updating knowledge of less frequently chosen base stations. And at the end, once these indices are calculated, this GJ are calculated for all base stations for that one single user, then we simply pick the base station that has the highest index at all times, whenever we're allowed by the block scheduling algorithm. The advantage of this is that our main result is we can prove that this algorithm combined has big O LNT total regret. So asymptotically, over time, we can show that this the total regret goes to 0. And this has the same optimal performance as perfect knowledge algorithms. Remember, we're comparing against an offline optimal algorithm with a priori knowledge. And so because mmWave changes so frequently, these time intervals are short, and we can show that 10 to the 4 time slots, in essence, 1 second, assuming 1 millisecond time intervals, we can already show our algorithm outperforms other existing techniques. Now we'd like to provide a little bit of experimental analysis. We compare our UCB-MS algorithm with 2 other algorithms, a baseline algorithm, which is a UCB algorithm that handles Markovian channel properties but does not handle switching costs, and the naive algorithm, where a user always chooses the base station that has the best last observed throughput. In figure A, we look at the total regret observed over time, and you can see that the UCB-MS algorithm certainly outperforms the other 2 in having a smaller regret. And even if you look at the slope of regret after about time 10 to the 4, you can see that the performance, the increase in total regret of UCB-MS is much smaller than baseline or naive. In figure B, total switching regret, you can see that, again, UCB-MS outperforms all the others until about 10 to the 4 time slots. This is an artifact of the naive algorithm, where the naive algorithm at some point simply does not switch anymore. Therefore, the switching regret does not increase. Hence the crossover at that point. In figure C, if you look at the total obtained throughput, you can see that the total aggregate throughput obtained by UCB-MS is actually much higher than baseline and naive. And one might ask, well, why exactly is that? Why is it that UCB-MS that puts additional restrictions on switching, on when you can switch between base station to base station, why can that get a better throughput than something that might not have that constraint at all, such as the baseline algorithm? And the answer to that resides in the fact that we use a much tighter turnoff bound than the example we found for the baseline algorithm, therefore allowing us better throughput. In figure D, we see that by increasing the number of users, we lower the average throughput on each base station, or each router of each base station, simply because there are more users contending for the same resources, and there's more regret due to exploration, and the slopes are much higher when users begin to increase their regret. In figure E, the total regret is decreased the better mmWave is. So say if we increase the instantaneous throughput of mmWave from 1/40th to 1/30th to 1/20th to 1/10th of the actual value, from green to red to blue to black, we can see that the total regret decreases from green to red to blue to black. In figure F, we increase the number of accessible routes from 3 to 4 to 5 to 6, and we can see that more options mean more regret for the user, simply because there are more options for the user to switch to. Thank you for your time, and if you have any questions, feel free to contact us at mw7@princeton.edu or changm@princeton.edu. Thank you.